Recording in progress.
Hi, Debbie. This is Hao Chung. Can you see the screen?
Recording stopped.
Okay, good.
Right, so Hao Chung is going to tell us about quantum channels. Well, stage is yours.
Okay, thanks, Yongchen. I would like to thank the organizers for inviting me. It's always my pleasure to come to the Q4 to give a talk. I really enjoy here. Okay. So today I will be talking about the one-shot coding for classical communication over quantum channels. And you can check the paper, the published version on PX Quantum. Okay, so let's first recall communication over quantum channels. Okay, so in the scenario of classical communication, we want to send M message over the channel from the message could be 1, 2, 3 to the capital M. First, we will encode the message to some multipartite quantum state raw on systems A1, A2 to the AN indexed by small m. Okay, then each subsystem will suffer from some IID quantum noise, and which is modeled by the IID quantum channel acting on each subsystems. So at the channel output, we got this noisy version of the state. Then we will apply some quantum measurement, which is a POVN, to get the estimated message. For a scenario of quantum communication, then we want to send the quantum state through the quantum channel. Then we'll do the same thing, but here we will use some CPTP maps to encode the quantum state into some multipartite quantum state. Then the same suffers from IID channels. Then we will use some another CPTP map to decode the quantum state. Sometimes we would like to protect the purification of the sent state to some reference systems. But today we will only focus on the classical communication over quantum channels. Then the famous HSW theorem tells us that if the rate R, which is the number of bits to be sent per channel, this N is the number of channel uses in the communication. If this rate is strictly smaller than the channel capacity, in this case it is also called a Holevo quantity, then the error probability will vanish as the code length n, small n, goes to infinity. So that's the known result proved by Holevo and Schumacher with Molen in 90s. But how to prove this HSW theorem? Well, you can check the Nielsen John's book in the last chapter, chapter 12, or Holevo's book. However, their proofs are quite long, and there are some subtleties in their proof. They are not just using naive typical projection and typical decoder, but there are some complicated analysis in their proof. Okay. However, there are also some technical assumptions in their proof. First, their result is an asymptotic result, meaning that their result holds in the limit of n goes to infinity. So essentially, they will require infinitely long large encoder or infinitely large decoder, which is quite hard in practice. The second concern is that the actual noise might not be identical, meaning that there may be some noise, correlated noise among several quantum systems. That's the second concern. Third, even if the noises are independent, they might not be identical, meaning that the noise acting on the first qubit might not be identical to the noise acting on the last qubit. So the underlying quantum noise might not be IID. So in recent years, many researchers are focusing on the one-shot quantum information theory, meaning that we only use channel just once. There is no specific structures on the underlying channel or state. So we are given a channel, a general channel, not necessarily IID from nature. Then we want to design an encoder and decoder to protect our sent message. So there are two questions. First, given capital N message you want to send, then how small is the optimal error probability we can achieve, which is optimization of all possible encoders and decoders. Second, if the optimal error is no larger than some fixed constant epsilon, and this epsilon is some error tolerance, say 10 to the minus 3, for example, then how many messages can we communicate through this content channel with error no larger than this epsilon? Then the number of bits to be sent is called the epsilon one-shot channel capacity. So in this talk, we will consider these two questions. A general recipe for studying one-shot quantum information theory is the following. We will first reduce a quantum information theoretic task to a one-shot quantum hypothesis testing problem. I will talk about this later. Then we will use some one-shot characterizations of the quantum hypothesis testing to evaluate how tight it is, or use some asymptotic expansion of the obtained entropic quantities. Again, there's no IID assumptions on the underlying channel. Okay, so let's first see some existing work on one-shot quantum information theory. Let's consider the most simple scenario of the classical quantum channel coding, where the channel sends each classical symbol to a noisy quantum state at the output. In this case, the encoder is just a classical encoder because channel input is classical, so the encoder is fully classical. However, at the output, the decoder is a quantum measurement. So in 2003, Hayashi and Nagaoka proposed a so-called Hayashi-Nagaoka decoder, and to prove a stronger one-shot result compared to the HSW theorem. And their proof relies on a powerful operator inequality. It says the following, but we don't need to have to read through this. So for every operator in zero and identity, and for any positive semi-definite operator B, then this operator inequality holds for any scalar, positive scalar C. And and here I use a notation I call a non-commutative quotient to, it's like a deviation for operators. So if you look at their proof, it works, but it's hard to interpret why this inequality holds and what does this mean, but somehow magically it works for achieving the Holevo quantity, but basically you learn nothing from using this operator inequality. You don't know why this is working. So the point in this talk is that you don't need to worry about this operator inequality because we never use this one. Okay, so the goal in this talk is to provide a conceptually simpler and intuitive proof by using the critical measurement, which is slightly different from the Hayashi-Nagaoka decoder. And it will give even tighter one-shot bounds compared to the Hayashi and Nagaoka result. Also, it will give streamlined proofs to other many quantum information theoretic tasks. So that's the goal of this talk. Okay, so let's go to the quantum hypothesis testing and proposed method. So what is quantum hypothesis testing or quantum state discrimination? So if the quantum system is modeled by, is in a state either in row 0 with probability, say, P0, or in a state of row 1 with probability P1, then the goal of quantum state discrimination is to perform a measurement, or call a test, which is described by some operator T and identity minus T. Then we want to figure out which system, row 0 or row 1 is. Then the Holevo-Helstrom theorem tells us that the optimal error probability for this binary state